Okay, hello. I'm going to talk about a new approach to software safety using STPA. A lot of my background is in safety engineering and system engineering with an emphasis on software, but I've come to appreciate that to get the software safe, we need to understand interactions outside of software as well. What we've seen in safety is a transition in the causes of accidents over time. A while ago, we used to be dominated by component failure accidents. In software, some of you may think of this as software not meeting its requirements. That used to be a big problem, but we've got a lot of techniques now to try to verify whether software meets its requirements. We're not perfect, but what's happened in accidents is that problem has gone down over time. Another problem has been growing in safety in general, and these are non-failure accidents. The vast majority of this growth has been caused by software. This is an accident caused when every component in your system works exactly as designed. Every single requirement is met, the software did everything it was created to do, and it still caused an accident. Here's an example. Some of you may be familiar with thrust reversers on aircraft. This is a device to reverse the engine thrust and slow down the aircraft. These are used to help it stop on the ground. Obviously, we do not want this to happen in the air. The plane will fall out of the sky. So we include software to prevent thrust reverser deployment in the air, of course. Safety critical, right? Sounds good. We have had many accidents caused by this software. For example, there was an A320. It landed, thrust reverser would not deploy. The software prevented pilot override, would not allow thrust reverser for 9 seconds, which is a long time. The airplane overran the runway and crashed and caught fire. Why did the software do this? Well, the software algorithm to prevent thrust reversers has two parts. For safety, redundancy, and diversity. First, it will wait for weight on wheels. That's one way to figure out it's on the ground. The other condition is to wait for the wheels to start turning. That tells you it's landed and is on the ground. And once those two conditions are met, the software will allow thrust reversers. Guess what happened? The sensors all worked, the software worked perfectly, and it crashed the plane because on this landing, we had something called a crosswind landing. Those of you who are pilots may know, in a crosswind, you cannot land straight. You must land crooked. It's called crabbing, and you have to land one wheel first on purpose so you don't flip the plane. Well, this is what it looks like. What does the computer see? The computer thinks the aircraft is still in the air. In combination, it has a backup. It will look at wheel speed sensors. Well, it had been raining. Guess what happens when you land in the rain? The wheels hydroplane. And this is what happened for 9 seconds as the plane landing. Both wheels in the air, one wheel on the ground, but the other is not. Software still waits until more than halfway down the runway. The software would not allow thrust reversers to work, and the airplane crashed as a result. What failed? Every part worked exactly the way we designed it to, but we did not anticipate these interactions. This is the fundamental problem, I think the most important problem we have today in software safety. Let's try something different. Instead of thinking about component failures, how about a simple control loop? Can this help us anticipate this kind of interaction? There was a control action. The software did not deploy thrust reversers. Why? Every controller has something called a process model. It's an abstraction. A process model is something you can think about before you've written the software. Process model is basically the computer's belief about the outside world. Why in the world would a computer not deploy thrust reversers on landing? What kind of belief would cause this? Well, we can identify this before we write the code. If it believes that there's no weight on the wheels, if it believes that the wheels are not turning, then it will believe it's still in the air and it will do this unsafe thing. Well, how can those beliefs occur? even when it is on the ground. It could be caused by component failures. We have redundancy for that. But it could be also caused by this exact situation. We may have been able to identify this if we had a method, if we had a different method for looking at this. This is a little simplistic, and later in this talk, we'll make this a little bit better. I'm just trying to introduce the idea. Another thing that we do very good is we look at individual components, one at a time. Very good. And that's what they did on this aircraft. They developed software requirements, react within X milliseconds, detect to tolerate sensor failure, respond only when multiple sensors agree, hardware requirements, redundancy everywhere, testing. How do you know what to test? You test the requirements, and they tested every single requirement, and every requirement was met. It worked. Test passed. In fact, if the software did anything else, it would have failed the test and we would have changed it. Everything we did before this accident was not able to detect the problem because it was not a failure. It was not the type of thing we're good at finding. In order to find this kind of problem, we have got to identify the intersection, the interactions between software and hardware and the environment. If we only look at one piece, we will never anticipate this problem, never anticipate that the requirements are wrong. This is actually pretty well understood in certain communities. Fred Brooks, famous computer scientist, writes, "The hardest single part of building software is not building software. It is deciding what to build. Building it is the easy part. Deciding what to build is the difficult part." That's the requirements problem. That has become one of the biggest problems we have in software safety today. Here's another case. That previous example was 20 years ago. We've learned, right? Here's a case from 2008. Almost the same thing. Aircraft was destroyed during rejected takeoff. It's a little bit different. During rejected takeoff means you start the takeoff, something goes wrong, you have to stop on the ground. You have to abort. Well, they tried to stop on the ground, and the reverse thrusters would not engage. They could not stop, went off the runway. What happened? Well, the tires disintegrated on takeoff. Not ideal, but it does happen, and we plan for this. What we did not plan for is that the computer ignored pilot commands for reverse thrusters. Why do you think the computer will ignore pilot commands on a totally different aircraft? Different software code. No line of the detailed software was identical. It was all different. But the cause was the same. The computer believed the aircraft was in flight. We had the same process model flaw. It gets worse. This computer was designed, if I believe the aircraft is in the air and I believe it's too slow, I will help. I will increase thrust. Worst possible decision in this case. But it was carefully designed that way on purpose, carefully reviewed, carefully tested, and it passed every test and every analysis. It operated exactly as designed. Let's try this. What if we used something so simple like this before the accident? What could we have identified? What kind of control action happened here? It was not on landing, slightly different. It was the computer did not provide reverse thrust on a rejected takeoff. A student could identify this in 2 minutes without knowing the accident. This is not hard. Next step, what kind of process model, belief, might cause this? If it believes the aircraft is in the air when it's not, this will happen. You can identify that before we've written any software, before you know what the requirements are. We can identify this. What kind of feedback will cause that belief in the computer? Well, if it receives feedback, that the aircraft is still is not on the ground from the sensors on the landing gear. That's how this can happen. You may have heard about the lithium battery fires on Boeing. This is a brand new battery. There's the one on fire. This is a picture at Boston where this happened on the ground. The fire got a lot of attention. I think that is not the most interesting part. The most interesting part nobody seems to know about because they're so focused on the failure. The most interesting part is the software flaw that was found. The software, even though they believed this fire would never happen for 10 million flight hours, that was wrong, by the way, but they designed it just in case, like good software engineers. They put two pieces of software. They put a fire computer to monitor for smoke. If there is smoke, the smoke can be vented into the cabin and the cockpit by a computer. So they put a computer to detect smoke, and it will turn on fans and valve to vent the smoke out. Right? Safety critical. They also, because of lithium battery technology, if the voltage is too high or too low, below 3.0 volts, we can actually cause a fire. So they designed a power management computer to detect battery discharge and do load shedding, turn off unimportant electronics. Guess what happened? This computer detected some smoke. This computer simultaneously detected rapid discharge. And this computer turned off electronics, including the ventilation computer. It never had a chance to work. We might as well have never built that computer and all of the software on it because of this interaction that was not anticipated or understood. We tested this very carefully by itself. We tested this very carefully by itself, and the hundreds of other computers were tested carefully by themselves. But altogether, we cannot test every possible interaction. And this interaction was not even known to test. This operated exactly as designed. If you look at every single requirement, it was met and every test passed. The same is true for this, but the interaction was overlooked by every software analysis, every test, every simulation, every safety assessment used internationally for aircraft, every design review, and every certification effort by the government. Nobody caught this. After the accident, we said it was a failure to incorporate the appropriate design requirements. Why are we having such a trouble finding these problems? Well, this is a very tricky problem. It's not a failure problem, it's a requirements problem. Can this help? What was the control action? There was two control actions. One was it did not provide a control action to vent the smoke. The other control action is to turn off the safety critical computer when there was smoke. Why would you provide a control action to turn off the safety critical computer? Well, it believed it was not critical. It did not have a high priority. It had a very low priority in the software. We have had a death caused by autonomous cars, unfortunately, in the US. There's the pedestrian. Some people have reacted to this and said, oh, this was completely that person's fault because they did not use a crosswalk. I don't know if any of you believe that, but if you believe that, you will never learn anything about software safety. Even if they did not follow the crosswalk, software is designed to stop anyway. Why didn't the software work? Well, we had cameras, may have been affected by low light, but we have other sensors. Radar and LiDAR, it should have worked. Why didn't it work? How many of you think there was a failure? How many of you think the software was designed to crash somehow? Well, first decision, this car was made by Volvo. It had something called City Safety, designed by Volvo, to automatically stop for pedestrians and objects. Uber disabled that function. Why? You may think Uber was stupid. Well, Uber wasn't stupid either. Well, They weren't very smart, but they made some mistakes. Every decision had a reason. The reason was they have the same function in their software, in the Uber software. They believed it was not needed. Another decision, they were very concerned that the Uber software may slam on the brake pedal and cause an accident from behind. So they made another decision. If the software commands hard braking, it will be ignored by the car on purpose because it could cause an accident. Now the reason was they were just going to assign the responsibility to the human. It will be safe, it's okay. It's just the human's job, not the software's job. So this decision was made. One more decision, the AI piece was so good at detecting objects that it commanded emergency braking every 2 miles. Too many false positives. So they made a change. How do we fix this? We will filter out the false positives. If the confidence measure from the AI is not high enough, we will ignore the obstacles. And that's exactly what was done. The AI piece actually worked perfectly. The piece that receives the AI output ignored the result on purpose, by design. Every piece worked as designed. All requirements met. The way we thought it should work was wrong. Very tricky problem. One more case. Let's just look for a second at city safety. Volvo does a pretty good job with safety, right? From their website, City Safety is a support system to help the driver in low-speed collisions. When driving, here's the picture. It will stop the car. Sounds good. Problem solved. Look, it works. Let's go home. Actually, it hasn't always worked. Here's a short video. If you do not want to see an injury, don't watch. Well, the video was a planned test of city safety at the dealership. The car was driven, a person was standing in front of the car. The car did not stop. In fact, it accelerated and hit the person. The person lived, but they were very injured. Volvo responded to this. The video is on YouTube, received millions of views. Volvo said, "This car has city safety." That is correct. Some people thought maybe it was the wrong car. However, it did not include pedestrian detection functionality that is sold as a separate package. It cost $3,000. Oh no! This exact problem has happened in aviation already. Northwest Airlines, when they purchased A320, there was an optional software package to sound a chime in the cockpit due to certain events. Northwest did not purchase the optional package from Airbus. Delta Airlines bought Northwest Airlines and kept the planes as is, and we had an incident where the pilots did not know what was happening because there was no chime. They would have had to enter a special menu on the computer to find this information, but there was no reason to check the menu system of the computer. This is not just an automotive problem, but it gets worse. Even with pedestrian detection, Volvo says it probably would not have worked because the software was designed to turn off if the driver steps on the pedal. Did the driver know this? Is this safe? Some people will say, it was designed that way on purpose. It's not a software problem. I think it is a software problem. In fact, if we look at all of the requirements for the software, below 2 miles per hour, it will turn off. You won't know it. It will just turn off. When parking, it is off. Over 30 miles per hour, it is off. If you steer, it is off. Certain traffic or weather, it will not work. If the other object is in the same direction, it will work. If it's in the opposite direction, it will not work. If you are backing up in reverse, it will not work. If the relative velocity is less than 9 miles per hour, it will not work. Is this safe? All these requirements were met. This is fairly well known. In fact, most software-related accidents are not due to a software bug. This is in the safety world. I'm not talking about website design. In the safety world, almost every accident caused by software has been traced to requirements flaws. Daniel Jackson writes, as is well known to software engineers, the largest class of problems is requirements. And of course, the bad news is this is the cost to fix a problem versus when we find it. All of these accidents have been found very late after the software was created, most expensive to fix. That's the bad news. The good news is they were caused in requirements phase. If we have better methods to find these early, we could find these before the software is written, when it is very easy to fix. But we need a method to do that. My last example, before I show you the solution, monostable shifter design used by most vehicles. If you're familiar with the Airbus side stick, fly-by-wire, this is the automotive version. This stick, it does not stay where you put it in a car. If you want to go to park, you go click, click, let go, and it will bounce back to the center position. This killed a person in the US because the human thought they put it in park, 2 clicks. They went 90% of the way to park, but not 100% of the way to park. Let go. No matter what happens, it will bounce back to center. So you cannot look at the stick to determine if it's still in park or not, if it worked. And the vehicle stayed in neutral. The person exited the vehicle and it rolled over the owner. That sounds like human error. What does this have to do with software? Well, it's interesting that this exact design was used by another company, Audi, but they had different software. Their software will automatically activate the electronic park brake if you exit in neutral, so the car will not roll over. That was a requirement that was missing from the first car that killed the person. You might feel like Audi did a great job. They have prevented the safety problem. Well, they've caused one too. What if you drive this car for 5 years and then you drive a different car? You may have learned, I don't need to go to park. This software will do it for me. It's very dangerous. Can this help? What about the human? I talked about software interactions. It works very well for that. What about human interactions? The human exited the vehicle when it was not in park. Why would a human do that? What is the human process model? The human believed it was in park, but they were wrong. Why did the human believe it was in park? Every piece of feedback we used to have in the system, including feedback from software, was removed. You cannot look at the shifter anymore and see where it's located by sight or by touch. The most important sources of feedback were removed from this design. We need to take responsibility for that in the software as software engineers and in the requirements. All right, so how can we do this? Part of the solution is we need a different model. We cannot look at thousands of lines of code to find these problems, and we don't have to. Instead of looking at detailed flow diagrams, instead of looking at detailed flow diagrams, we're going to recognize that there are control relationships in the software. These things are being controlled. These things are deciding which way to move. We're going to abstract into something much simpler. We have control actions to affect some process. We have feedback used by software to monitor what is happening. We have a process model, a set of beliefs formed in the software about the outside world, and we have a control algorithm. Given those beliefs, what does the software do? We need requirements to cover all of these, and we need to identify flaws in all of these areas. In fact, in a real system, you have more than just one control loop. You have a hierarchy of control. This is something called a control structure. We have control on the vertical axis. Boxes at the top have control over boxes at the bottom. That means downward arrows are control actions, commands, instructions. Upward arrows is feedback, information about the world to make decisions and form beliefs. In fact, we would not want to start here in the detail. That whole piece that we're building, we can put that in a box first. If we want to know if this is safe, first, we must understand how it will interact with the operators, how it will interact with the aircraft and the transmission and the physical components, and derive requirements on this entire piece as a whole first. In fact, maybe this is the component view. This is how we have missed all of the accidents I talked about. This is a systems view. This is what we need to prevent these kinds of problems. In fact, maybe we don't want to start here at all. We want to start at the larger system. Maybe this is a ground station that's being used by a joint command, and there are interactions and contradictions between these different entities that we need to create requirements for first. Okay, now it's time for the method. Now that you understand the problem we're trying to solve, here's the method to solve it. There are 4 steps. You begin by identifying losses, what we want to prevent. Then you build a model called a control structure. Then you analyze the model. You start by identifying unsafe control actions. These are downward arrows that are unsafe. And then you identify scenarios, step 4. Step 4 provides an accident before it happens. It tells you exactly what requirements you're missing in your system and what interactions you haven't thought about yet. Let's start with losses in aviation, maybe loss of life we want to prevent. STPA will now find every possible software cause of loss of life. But we could also include damage to the aircraft. That's another loss. What about loss of mission or transportation? That's another loss. I know this is a safety conference, but NASA has a safety program for unmanned Mars vehicles. How? There are no people. Safety does not just mean loss of life. It means preventing a loss. For NASA, safety means loss of mission. Or we can look at loss of performance. We can prioritize these. Every result from STPA is traceable to one of these losses, so we can prioritize the requirements and the test cases from STPA and the flaws that we find. What about automotive? It looks very similar. We can also look at loss of customer satisfaction. Maybe we do not kill people, but we frustrate the driver because they cannot control the car. They cannot start the car. Nuclear power plant. There have been a number of STPA examples in the US. Nuclear power is now being used for certification in nuclear. It's very similar. Loss of life or injury. Equipment damage. Maybe we need to include environmental contamination. Loss of power generation. STPA will find every software cause of these losses, whether the requirements are violated or the requirements are met. By the way, is this safety or security so far? It's both. There's no difference. A lot of safety methods have nothing to do with security. That's because they start with component failures in the details. But we're not starting in the detail. We're starting in the objective. This is really a method for mission assurance. Safety and security are causes of mission assurance problems. In fact, I'm going to talk about safety in this talk, but every single step applies to security as well. Control structure. This is what it might look like for aviation. We may focus on the bottom if we're creating software, but we can also look at flight crew controlling the software. And what about air traffic control? We just had a crash a few years ago. Asiana, San Francisco, Boeing 777 crashed. There was a flaw in the software that was triggered by an interaction with the flight crew that was caused by an air traffic control instruction to slow the plane. If you're familiar with aircraft systems, this is a little more detail. This is all of the software automation on an aircraft. We can look at those control actions and the feedback. Adaptive cruise control. In cars, we have radar, so that piece of software can control brakes and throttle on a car. Here's the software. The software can command brakes and acceleration, can monitor speed and distance. The driver can turn it on or off. It reports. We can analyze this with STPA and create black box requirements for this software, and then we can zoom into the software and look at the different software functions. Here is a fully autonomous aircraft. It looks almost the same as a fully autonomous car, by the way. Here's an operator who may send a destination. A mission controller sends a waypoint selection, trajectory, and then individual controls of the physical parts of the aircraft. This is the control path. Here we have feedback path from low-level sensors to high-level information about objects and movement. Next, unsafe control actions, step 3. With the control structure, we look at the downward arrows. These are control actions, and we identify how they can be unsafe. This is a software control action, and we look at 4 cases for a command to be unsafe. Think of a brake command provided by a computer in a car. The brake command may not be provided when there is an object that could be dangerous. Brake command may be provided in a highway or in an intersection when it is unsafe. Brake command may be provided too late. That could be dangerous. And last, the brake command may be provided in the right situation, on time, but you let go too soon. You step on the brake in the right situation, but you let go immediately, and it's not effective. This is provably complete, and we can analyze these with STPA. There's a lot of detail that I'm not explaining. I will give you a reference for more information. For example, these unsafe control actions, let's look at this. Computer does not provide reverse thrust command when aircraft lands. There are 4 parts of an unsafe control action to make sure we're being very careful about this. A source controller, where does it come from? What piece of software? Type, was it provided or not provided? Both can be dangerous. What was the control action and what was the context? And we can use this, specify them in a machine-readable format, and we can generate the necessary software requirements in your system. This is an easy case. You can do this one by hand. Computer does not provide reverse thrust command when aircraft lands. What's the highest requirement then for the software? Computer shall provide reverse thrust command when aircraft lands and reverse thrust is armed. And then, of course, we need to refine this requirement to determine how it will detect the landing. Here's what you get from all of these unsafe control actions. You get 4 kinds of software requirements. Shall provide command when D. Shall not provide. I know some people don't like this. You may not be able to test it, but it is important for safety, and it will be used when we make design decisions, not just for testing. Computer shall provide command within Y seconds. That's a timing requirement. And shall stop providing within Z seconds, a timing duration requirement. We have one more step. Even with those requirements, they could still be violated. For example, the software may be following its requirements, but something may lie to the software, and the software does not know any better. It may not be smart enough. We need to identify these scenarios and determine how unsafe control actions could be provided. For example, computer incorrectly believes X because control algorithm does not enforce Y because. From this, we get design recommendations and component requirements. And for every single requirement, We have the rationale. We know exactly where it came from. We have a specific accident scenario that we're trying to prevent. So if you ever need to make a change later, you know where they came from. The exact same process applies to human interactions. Instead of human requirements, we call these procedures. How do you know if you have all the right procedures for a human? If you're only interested in software, what assumptions are you making about the humans that use your software? We have had many accidents caused by software engineers making bad assumptions about the humans. This is a way to document your exact assumptions about human behavior and make sure it's included in the procedures. We also would look at why the flight crew or the human would make these bad decisions. If you're a software engineer, why do you care? Software can cause human error. Many people don't know that. Human error is not independent. It's affected by the context. Human error here can be caused by software that lies to the human or provides misleading information. We need to take responsibility for that when we create software. But we have very few methods to help us. Here's the whole process. 4 steps. Start with the losses to prevent, build a model, identify unsafe control actions, and identify scenarios. These are accident scenarios. This is a small accident report before it happens and before you've written any software. Traceability from every result is maintained in STPA all the way to the high-level losses and accidents. Let me do a short example. Let's pick something extremely simple so we can do it in 5 minutes. Let's do Google's entire self-driving car. We can do that because we're starting at a high level. We do not need to look at thousands of lines of software code to analyze this. Let's try it. Step 1, identify losses. Well, we can use the ones I already showed you. Let's look at loss of life and damage to the vehicle. Let's find how the software can cause these things. What kind of control structure might we use? Well, at a very high level, it might look like this. Even though it's an autonomous vehicle, there is still a person in the car that can provide an emergency stop command to the software. The software can provide commands to change lanes, to go, to stop, and so on. Here's some feedback that may be provided. Next, let's identify the software control actions that we need to prevent, the unsafe control actions. We would fill out this table. Let's look at the lane change command. How can providing the lane change command cause an accident? Well, here's an example. For a driver provides park command when vehicle is moving. That's for human interaction. What can we do for software? Follow the same process, and we'll have autonomous software provides lane change command when object is in the path. Clearly, we need to prevent this unsafe control action. We're not done. We need to find how this can actually happen in the software. So let's start here. Here's the unsafe control action. Autonomous software provides lane change command when vehicle is in the path. What would the software have to believe to do this? You can answer this without looking at the software, without knowing what the requirements are yet. You can do this on day 1, very early. There are at least 2 beliefs we might think of. Number 1, it believes there is no obstacle. Of course, it's going to maneuver if it believes there is no obstacle. Number 2, if it believes there is a vehicle, but it's far away. Right? And there may be a couple others. Okay, let's look at number 2. How in the world would the software incorrectly believe it's far enough away? What does far enough away mean mathematically? Because that's what software is, math. How does the software going to determine far enough away? Well, if you remember back to Physics 101, the kinematic equations can tell us our answer. Here's the kinematics equation. If you solve this equation, you will find basically if d is greater than v squared over 2a. V is instantaneous velocity. That comes from a sensor. D is distance to the object. That also comes from a sensor. What about A? A is actually not acceleration here. It's deceleration capability, if you think about it for a minute. It's basically about the reaction of the other vehicle. It's not enough to compute that it's on a collision path. You need to know if it has enough time to stop. Here's a way to think about it. If you are driving along and there's a small car behind you, you need a certain distance to safely move in front. What if it's not a small car? What if it's a giant truck or bus or a train? You need a much larger distance because it can't slow down as fast. The deceleration rate of a train is very slow. That's A. So Google knows this. Google did this in their car, and they found V comes from the sensor, D comes from the sensor. A is a little weird. Future deceleration of the vehicle, that doesn't come from a sensor. The closest we might be able to do is the size of the vehicle and estimate. But it turns out these sensors and the machine learning algorithms are pretty good at detecting an object, not good at classifying the object. They cannot tell the difference between a small car and a big bus reliably. Google knew this. So what they did is they made an assumption. Let me talk about that in a moment. Let me move on. So we can look at causes for each of these, not just if these measurements are wrong, but we can pinpoint the exact type of problem. If measured distance is too high, if measured velocity is too low, or if the deceleration capability is too high. Now, this is interesting because this is exactly what happened. We had a crash caused by a Google car that followed this exact scenario here. What happened was the car was making a right-hand turn. It detected these construction cones, and that caused the software to merge left. It merged right into a bus. Why? Well, it detected the bus. The bus was not in the path. It was behind. But it did not know the bus was big, and the bus could not stop quickly. What the software engineers did at Google is this comes from a sensor, this comes from a sensor, this is a constant because it does not come from a sensor. We can't get it. So they programmed the constant. What constant do you use? They used an average deceleration capability for all vehicles. And guess what? For about 5 million miles, it worked. It was only in this very specific case where it needed to merge left, and there was a bus in exactly the right position. And then we had this crash. So what is the easier way to find this flaw and fix it? Drive the car for 5 million miles? Or do a very quick analysis like this using STPA and get the requirements right? We could have generated a requirement that said, if you do use a constant, it needs to be the maximum value, not the average value. And we can have similar constraints for these. Or if you already have requirements, we can check them and see if they're correct and needed. I'm going to skip this one. We did the same thing for Tesla Autopilot. Maybe I'll just show you one. Yeah, I'll just show you one case. This is the end result of STPA. Here's the Tesla car. Here's the car behind. This is how software can cause a human error and cause a crash. Software is driving along. Here's the unsafe control action. Driver grabs the steering wheel and forces it to crash. That's the UCA. Why do we care? This is a software conference. I don't care. That's a human error, right? You care. Here's why. We used STPA to determine how the software can cause this. Here's how on a real Tesla. If your Tesla is driving down the road, it uses cameras to find the painted lines. If the painted lines diverge, which one do you follow? There's no correct answer. Tesla decided to follow the one on the right. So if you drive down the road and there's an exit ramp, the car will automatically start to take the exit. In 2016 anyway, when this analysis was done. Now, another piece of software is intelligent, uses a camera to detect the speed limit sign and automatically slow down the car to match the new speed. This is a very low speed. Nobody goes this slow. But Tesla will. The software will. Aha, we have it. Do you see it? Here's the scenario. Your Tesla is driving along. It automatically takes this exit ramp and applies the brakes. You're in the Tesla car. What do? Uh-oh, I don't want to go that way. You will probably grab the steering wheel, override the automation, and steer into the other lane. But how does that get a crash? How do we get a crash out of that? Well, imagine a human driver was here when this started. You take the exit ramp and slow down. When you grab that steering wheel, where is this car going to be? It is possibly going to be right in your blind spot where you cannot see it. This is a scenario that was created by the software decisions on a Tesla. Now that we have identified this scenario, whether you still think it's human error or not, there is a human contribution, obviously, but we can also make the software better and prevent this. We can check the requirements we have and make different decisions. Here's a similar crash. That's a Tesla. Do you see why it did that? The software worked. Do you see why? The software was following the painted line right here. It followed the painted line. That barrier was at an angle, and it may not have been made out of metal, which creates a weaker radar return. The software may not have detected the barrier because it was at that angle, and because the painted line continued forward. Maybe I'll show this. This is a quick one. Videos are working now. The driver took control to stop. Why did the Tesla car do this? The software followed every requirement. Watch carefully. See these lines? These tell you which painted lines the computer can see. The computer follows the one on the right unless it is not detected. The line on the right was lost, so the computer followed the line on the left. It could have easily been a crash. Okay, I'll go very quickly. STPA has been adopted in the last 5 years by an incredible number of companies. Embraer is using this now on new aircraft. General Motors is using this. 2018 vehicles are based on STPA requirements to find these problems. Boeing has a list of about 15 applications that they're already using STPA on. Rolls-Royce, the aircraft engine manufacturer, applied this and found approximately 30 additional items on a system that had been in flight test for 2 years, had already passed every software safety analysis, and they found 30 software causes of this problem using STPA. Here are the automotive companies that have already adopted STPA for software safety. GM was one, and Ford were some of the first. Now it's used by Toyota, Volvo, Nissan, and others. Semiconductor manufacturers as well. I added these because I gave this talk at an automotive conference, and some people from Texas Instruments and Analog Devices were very upset with me for not being on this slide, so I agreed to add them. It's being introduced in 6 industry standards in automotive, aviation, and nuclear power for software safety. And it's being used in medical devices, defense, space, nuclear, and rail. This is my last slide. For more information, see our website. We have an STPA handbook. It's free download that will tell you how to use STPA for software if you're interested. We also have a conference in March. We don't charge any money. In fact, we'll give you a free dinner. You just have to come and learn. It's a users meeting. It's not an academic meeting. It's from people around the world at companies applying STPA and sharing their results. There are training classes. And if anybody has any questions or comments, please email me. You can find me on LinkedIn. I'd love to connect. Thank you.